And I am pleased to welcome our next speaker, Irena Hajnsek. She's a professor of Earth observation at ETH, and we will go slightly more towards applications and how AI can help with Earth observation application products. Irena, the floor is yours.
Okay, great. Starting here. So yeah, welcome to this presentation. I'm very happy that Mark was giving this really very broad overview of what you can do. I will focus more on products, really this downstream task, as there was already also a question here, how to transfer actually all this geospatial information into really kind of products and variables. Yes, and I'm focusing here also on one specific remote sensing. Earth observation is very broad, so when I was reading this session about Earth observation, I need to say that I'm focusing really here more on SARS systems, which is more on the radar domain, where we have longer wavelengths on, and the physics are a little bit different as using, let me say now, optical systems. I would like to acknowledge my co-authors, Nikita, Islam, and Shi. These have been my PhD students, where they have also contributed to some of the slides. Okay, just to go a little bit, it's clear in terms of, and this has been also shown by Mark, we have quite a lot of societal challenges that we would like to see in a global dimension. And you know probably all of these kind of tasks here: climate change, environment, resources, sustainable development goals, for example, how to map them, and how we can provide information content, right, to all of these kind of societal challenges. And I have some example how Earth observation can really do this, and this provides you also a little bit of view. When I'm talking about radar data, then I'm talking about physical properties that are behind this radar data. With radar data, what we can do in the first example, we can measure velocity, right? Velocity is something that is very difficult normally to measure in optical domain and radar data, because we are an active system, we are transmitting and receiving signals, and what we can do using interferometry, we can make a phase difference, and between the phase difference something was moving, and this is what we can observe. So glacier movement is one particular indicator also of climate change, as here, or even mass balance. If you like to know, a mass balance is also something that can be estimated very well. What is also different is if you go for deforestation, we are penetrating into a volume, so which means we are getting information about the surface, but also the whole volume content. And then not only, if you look for optical data, we are getting mainly what is on top, right? But here with radar data, we are penetrating. What you see here is deforestation, and that's very interesting because the white part is actually the real tropical forest. The blue part is a cutted part, but the pink one is the one which is already cleared in terms of prepared, that we have later on bigger instruments or vehicles coming into the forest which are cutting then the trees. So this is a preparation for clear cutting. And if you know this with Earth observation, we can observe this. If you know this, you can go to the offices and can tell them, look, this is something in preparation, and we can see this from space. Is it legal or illegal, right? So something like this. We can do, what we also derive for resources, what you see here is a digital elevation model, right? The digital elevation model derived by solar interferometry, where you see heights, and heights can provide you information content. You will see a very deep mine, it's a copper mine, and beside you see the deposit of material that has been not used. So this is something that you can really observe. What is also great with radar, you can see movements, not in terms of glacier movements, but here subsidences. So you can see movements in the accuracy of millimeters, right? You can see how the Earth is breathing. And that's something that is, I would say, very amazing to see this from space, where you are around 500 to 800 kilometers far apart, right? So you see things that are happening here. That's an example over Mexico City. The red area is the strongest movement that you see, and then it's fading out a little bit on the border. This is done actually, or this movement has been observed because beneath Mexico City we have a groundwater reservoir, and this groundwater reservoir in times where you have less, let me say, rain ongoing and a lot of pumping of groundwater, so you move down, and in times where you have rain, a lot of rain, you refill it and you move up. So this is something very nice to see. Urban planning is clear, there's nothing else than classification, as you know already, also in other kind of optical data we could do also kind of traffic monitoring. It's still a new, I would say, part. It's not so easy to get it because you need observation from different incidence angles, so there's still something that is still ongoing. But what it's used really is for any kind of hazard. So earthquakes, volcanic eruption is very important. Here you see a digital elevation model where you see now the cone or the part here, the round part, which is visible very well when you use radar data, because normally when you have eruptions, you have a lot of smoke and dust ongoing, so you can't really see what is beneath happening and how big is actually the mouse. And it is used, but that's for disaster, any kind of data I use, not only radar data, but like these, you see already differences in terms of physical properties that are different from using optical data, where you use mainly statistics to observe kind of physical parameters. I would like to focus today on 3 parts where we are using, so we are more the users of AI in this case. So one thing is using for product generating a hybrid, i.e. physical framework for model inversion. So in this case, what we really do is try to train a model using AI. The second example is going a little bit into the direction using AI, but then constrain it physically based. So this is something for soil moisture. This will be the second example. The first one is forest height. Sorry, I was not mentioning this. And the third one, and this Mark was already saying, how you can use also a foundation model, in this case probably a geofoundation model for any kind of classification that could be useful. In this case, we use it as an example for superglacial lake classification. Okay, let us start then with the first one. So just to have a little bit different approaches. So why using forest height? So forest height is one of the key parameters for to estimate above ground biomass. How you do this? Normally, every forester is doing this too. You have the height, and out of the height and the density of the wood, you can estimate, or you can have an allometric estimation of the biomass. And this is how the relation is between a physical parameter, which is height, to something that is related to above ground biomass. And it is also one of these essential climate variables that you have. For this, we're using Tandem X data. Tandem X data are, it's a mission, it's a German mission, which is a bistatic mission, which means we have single pass interferometric acquisitions over global coverage. And what we could do, so we can use it also, I mean, we have a model behind that I was showing later on. We can use it also and using this data and directly inverting it with a model, with a physical-based model, using without AI. But here, potentially, we have also some biases, and therefore we try now to use AI to train actually our model. Yes, in order, so what we need is then need more, in this case, we need the methods to integrate knowledge and domain knowledge and generalize across sites. What you see here is a TandemX coherence map, so that's not the radar backscattering map that you probably used to, but this is really an interferometric map, which you see is varying in terms of colors and gives us, in principle, it's a parameter which gives us structural information. So structural information means information about the forest itself. Okay, that's just to see above ground biomass where it exists. So interferometry is actually very easy. So if you have 2 satellites, right, you have it, in principle, you have a certain distance of these 2 satellites. You're observing the same part of the Earth's surface, and what you can get out is your height estimation. So this is what you normally do using the phase difference here. And we developed a model which is using this kind of parameter, this you see here below, which is in principle providing you estimation of the forest height. What you do, you model the coherence. This is what I was showing before as an image. You model the coherence. The gamma volume is a model of the coherence itself. And as a main function of this model, we have forest height. This is one thing. We have the vertical reflectivity function, which is important. And the vertical reflectivity function is f of z, you see it here, is providing you information about the structure. So in principle, this model tries to provide you because you penetrate into the forest and you get, depending on the interaction of the volume and the electromagnetic wave, you get a kind of a structure function. And with this structure function, this is one of the main parameters in order to model my observable, which is the interferometric observable. And then what you also need is a capacitor, which is in principle the distance, the geometry of the two satellites to each other. So it's a distance between them, because varying this distance, you get different sensitivity to your height on the ground. So this is why this is important. That's very easy. You use the first image, the second image, you do a cross correlation in principle, and then you get your coherence, which you can also model it here physically based. But let us now see how we can train our model, because that's the main idea behind. So we are using a very simplified, very simple model in this case. You see we have expanded, I don't know, is there a pointer? Not pointer. So what you see is the features of our INSA observables, which are our coherences. We integrate this into this multi-layer perceptron. Then we derive this vertical reflectivity function, which you see here, and we integrate this then in this blue part, which is in principle the physical model. So we use already the vertical reflectivity function. This is something that we like to derive. We integrate it into the physical model, and then we do in principle an iteration in terms of using the minimum distance between the physical model and the multi-layer perceptron. Let us go further on to see how does it look like. So we do some validation here. I'll show you some validation on the test site, which is in Gabon. So it's a very, very dense forest, tropical forest. We have 3 sites here. We have started to work on one site, which is called Lope. And on this site, you see now here the coherence image, and you see the reference data just to compare and to see how good is the validation later on. It's taken by an airborne LiDAR measurements, which is Elvis from NASA. Okay, let us go now to the coherence. How good can we estimate the coherence, where we are deriving the vertical reflectivity function? This you can see here. We have the coherence against the capacitor in terms of the capacitor and height. So this would be the relation that you have. So it's kind of linear relation. And the second, then we integrate these coherence now in order to invert it. And then the height that are inverted are now on the second image. You see the estimated height against the reference, the LiDAR reference, and you see we have a quite good, let me say, cross correlation between these estimate. What you get also, because it's a physics model, you get also an error. Let me say an error estimate, which is important to know where are the points where you potentially have a stronger error than other regions. And below you see here this forest height now as an image, as a product that has been generated. What we have also done, we used, as said, Lope as one of the training, so the test data set, and then we have applied it to the other test site, which are a little bit different. So Lope has a mixed forest, has also savanna patches, so it's a little bit a mixed kind of forest. And then for the other one, these are more denser forests in this case, which is Mabuni and Rabi. We have applied the function that we've trained on Lope and have applied it to the other one, and these are now the results. Again, a correlation function between the estimated against the reference, and we are quite good in terms of that we get good results for forest height estimation. So this hybrid model is actually quite great because we can understand where it's going wrong, right, and where it has problem, because we have a physical parameter behind. And what is also nice here, it can be very, very well transferred also to other regions. Okay, this was my first part where we train a model, a physical-based model, and now what we do, we use AI and constrain AI physically based. And this we do on the soil moisture estimation, also soil moisture, we call here surface soil moisture. I'm always asked, because I'm teaching at the environmental engineering department or institute, and they would like to see soil moisture which is going down to the ground, to the, let me say, to the water, to the table water, but normally this soil moisture is really only on the surface. So what we are talking here about is a few centimeters, therefore soil moisture more on top of the surface. However, the main challenge in estimating soil moisture, there are a lot of soil moisture map and very low resolution available. There are satellites which are providing this, but all of them have the problem of the presence of vegetation. So if you have vegetation, you're not estimating soil moisture, but you're estimating water plant content, right? Because you are sensitive to the plant water content that is changing, and specifically very strongly over agricultural field. You can have bar surfaces, but you can have, as here, irrigated areas, and then you would get estimates about the plant that has been irrigated, so all the water droplets on the plant. And what you see below is if you really have very, very strong corn, so this is 2 meter to height, so this means you have a strong influence if you go for high resolution imaging, and this is what you like to do. Okay, let us go with the data sets. Here I have chosen another data set. It's not a satellite, but it's an airborne sensor that we use. We have 2 test sites. The one is close to Munich, estimated or acquired, which is Cropex. And the other one is Hydroterra, which has been taken, the acquisition in Italy. And what is now here different is we do not use only the radar backscattering intensity, but what we try to use is the scattering mechanisms. So scattering mechanism means how it works, right? How is the interaction of the electromagnetic wave with your property? It can be differently because we are penetrating. You can have surface scattering contribution. You can have multiple scattering in the vegetation, which we called volume scattering, or you can even have dihedral scattering contributions. Dihedral means you have an interaction of the ground to the plant and then coming back. And this is here in this color coding that you see different mechanisms that are appearing and that are stronger. So everything that is popping up stronger here in terms of colors is in principle the scattering mechanism that you can see. Okay, we are looking here for longer wavelengths. Why longer wavelengths? Before we have been in X-band with 3 centimeters. We are not penetrating so strong, but in L-band is 24 centimeters, so even stronger penetration into the volume, which means you get more contribution probably from the ground than really from the vegetation. But still, I can tell you, you have contribution from vegetation, and this is what you see here. Everything that is green, it means you have a lot of volume scattering, and volume scattering means you have contribution from your vegetation and less contribution from the ground. Okay, let us see what we can do with these kind of data sets where you have a lot of vegetation on top. You could start to work on the supervised machine learning where you have these input features. For example, what we use, because we use in polarimetry, we use coherency matrices and the incidence angle, and then you can do, in principle, you can transfer or map this into the predicted parameters as, for example, what we like to have or obtained as soil moisture. You can also do it only using a physical model, as we have seen it before. You have, in principle, your parameters, so the input physical parameter, you have a physical model, and then, in principle, you predict your coherency signal. What we try here now, and this is what I explained before, is we try, in principle, to combine both things here and to constrain or to have a physical autoencoder to constrain actually the IE with a physical-based model. And therefore, we see on the first part, we have a kind of self-supervised training on unlabeled data, and we use a hybrid fine-tuning, or it's possible to do this here. Then we derive, in principle, our parameters here, which is in the latent space, and it contains only the physical parameters, and these are then mapped in the model, in this physical model, in order to derive the coherency matrix, which in principle, what allows you here is in principle explain the explainability. So you know exactly each parameter that you had as an input, and you can explain what you get as an output. Here is now some of the results that you see. So we have certain amount of different methods that we used here and trained. So the one is a very simple supervised machine learning approach, and the second one is a hybrid autoencoder approach. Then we have the self-supervised one that we suggested. So the hybrid one is where you train, still use the training on the data, but the self-supervised is without any kind of test training. And then you have only the physical model. So you see already, if you have all the information that needed, because for the supervised, what you need is a lot of training data. You need to know the soil moisture in order to train the data. You need to know the incidence angle and all these parameters. If you have enough of these parameters, then go with the supervised classification in this case, or modeling, that's fine. But if you don't have it, and this is actually in principle here seen on wheat on top and on maize below, then you see here the hybrid or even the self-supervised approach looks quite well. So that's always, sorry, I was not mentioning, it's always a correlation plot between the soil moisture from maize or wheat against, in principle, the ground measurements that we have done on the field. Okay, and in principle, the main message here is if you don't have enough training data, right, in order to train your data, then a model and a self-supervised approach works very well, actually, in this example. Okay, the main outcome, probably just to see it again, now over one field, you have in principle the parametric information with the Pauli RGB. What you get also, and this is important, you get in principle a composed power, which provides you a ratio between how much ground to volume you have in order to be explainable. How good are your results? You like to explain how good are your results. We would like to go on quantitative estimates, so we would like to have a measure behind it. And this second row is in principle providing you as the estimation how much vegetation to ground I see in my images. Then you have the soil moisture estimation and the reconstruction error. And if you now compare how much vegetation you have and how good your reconstruction error is, then you see you can in principle explain your data much better. For example, on top, we see we have a little bit, in the middle, we see we have a little bit greenish, and greenish means volume, but you see also bluish part, which means we have a lot of surface too. And then your construction error is a little bit light red, which means, okay, I can still explain, I can explain it in terms of the error is not so high. However, if you go very on below for cucumber, you see it's very green, means a lot of volume on top, right? And if I have a lot of volume, then my error is also increasing. So this is a little bit how you can then judge your soil moisture estimate. So in principle, make it explainable. That's the main part here. Make it explainable and have a kind of estimation error on it. My last example is going to the geofoundation models. Here the example is classification using glacial lake classification. Glacial lakes are important for the dynamics, to estimate the dynamics of the glaciers. I mean, that's important. And therefore, lake mapping is very useful. In this case, what you see here on the first row, these are images from radar, but also from optics, and you see already how different they are looking, right? You see an optical image completely white, where you have already a classified shape around it, and the first one you see really a difference also between, it's a radar image between the lake, which is frozen, and the surrounding surface. But glacial lakes has very, very different features. You see it here below, can be blue ice, you can have topographic shadow, you can have crevasses, or even wet snow on top, right? It's a very, very complex region in order to really detect it or classify it well. But let us see how we can do this using now this geofoundation models. We have here two test sites. The one is in North Pakistan, where we use optical and also radar data, so it's a combination, Sentinel-1 and 2. And we see also in West Greenland, we have also some test sites here. And this is taken only by a radar mission, which is a Chinese Gaofen 3 radar mission. It has same spatial resolution, so we hope that's fine. What we have with the Gaofen 3 is also diversity in terms of polarization. This is what we saw before. If you have polarization, you can estimate with the physics behind, so the scattering mechanism, and this is seen here, the different color representing in principle different scattering contributions that you can see. So the physics behind this observation. We use a very simple model architecture. This is a U-shaped on the one side, so this encoding part is based on the backbone model of Prithvi. Everybody probably know Prithvi is mainly based or trained on optical data, and then the decoding part is a classical decoding part, and we have two parts on top, which is this enhanced squeeze excitation and the inverted bottleneck block, which is in principle shaping the data, compressing them and decompressing them to the layer that are needed and can be ingested into the model. Okay, let us go to the results. We see now on the first image, this is an optical image. This is from North Pakistan, and we see the second row is our ground measurements, and then the third row is actually the model that has been proposed or taken in this case, the GeoFoundation model. And you see for some parts it works quite well, for some probably not so good. And then we have as a comparison also other other approaches, UNet, DeepLab, V3 Plus, or the MANet. And here, the West Greenland is the same. So if you look now to the ground truth and to the proposed part, for some region it works, and for some not so good, right? So that's what we see here. And if you go a little bit into statistics, then we can see in general that for the North Pakistan data, we see data set, we have a quite good proposed, we have a quite good proposed statistics here for the precision recall, F-score, F1 score, MIU or AOA, but for the VGL data set you see here, it's not so good. So even not the proposed one, but another data source is much better. The point here between these two is actually quite good, because for the Greenland data, if you remember, the Greenland data have been only taking radar data, right, from a foundation model that is based on optical data. So, and if you check this now a little bit, and this you see in the lower table, if you take out the near infrared part, right, for example, then you see that you have a quite strong degradation. So it means that for a combined data set, where we have optical data and radar data combined, then it works better as if you would only take, in principle, radar data. And so for some of these, therefore, we have the problem of the reconstruction. So therefore, depending on which kind of model you use, the missing of information of the training actually of these data sets is very important to have in principle the same physics or statistics behind for these two different kind of data sets that we have, the one optics and the other one the radar data. This is now just to see again the supraglacial lakes. The red lines are in principle boundary with public data, and the blue lines the red lines is in principle from the what we have estimated with the model, and the blue lines are the public data that has been circled around. And what you can see here specifically below, so mainly it fits very well to each other, but if you look below, it looks like that even for the method that we use, it is better to use in principle the machine learning approach than using the boundary line, because it fits much better to the shape of the data. Okay, that's in principle all. My take-home message here is in principle just to show you what is also important for us as a user, right, is to take it to have an explainable, or in principle to have an error message or an error indicator behind, in principle, each of the product. That's important for us in order to see how good is my product quality. And therefore, we think there's a benefit of using physics-informed IA. It is accurate, it can be interpreted. I think that's most important, to have an interpretable and transferable regression. So that's important. And what is also important, embedding physics in IE reduces also biases, is what we have seen, and improves this generalization. That's also something that is important. Specifically, it's clear also that the physics model needs to be also accurate, right? If the physical model behind is not good enough, so then also the generalization doesn't work so well. Okay, and for a geo foundation model, yes, I think there's still some way of improvement here. The new version, it's clear they have also a combination of optical and radar data, and like this, I think it would fit better to any of these electromagnetic spectra much better as it is in the moment. So this was only to show you that is always depending what kind of data you use and which kind of downstream task in order to have it more well done. And then for an outlook, we still think that IE helps a lot. It's a very, very powerful tool, actually, to use IE, but the physical models are also very great because they are explainable, right? And when you combine both, the explainable part with a powerful tool, this combination is actually where we need to go forward in order to have really triggered all these essential climate variables that we'd like to get as a product and to have an error estimate on top of this. Okay, thank you very much, and that's actually my last slide here.
Thank you very much, Irena. Okay, I will just take the questions closer to me.
Thank you very much for the talk. I was wondering, in terms of soil moisture, what do you think is the state of the art, and what can we see maybe developing in the future that can get us closer to estimating more accurately soil moisture from using remote sensing data? Or what maybe if it's a data fusion matter, what shall we consider to improve this product?
Yeah, as said a little bit, I mean, soil moisture, as said before, there are products available. They are just in a very, very low resolution scale. So they have 1 kilometer and then even up, right? So very, very low resolution. And the problem is if you go for low resolution, it's easier. Because what you do, you smooth out the vegetation, which is a little bit something that is disturbing you, right? They're considering then that the vegetation doesn't play such a big role if you have such a low resolution, which is fair, and probably it fits. But what we like to have, or at least the farmers, what they like to have is a high resolution product. They like to see it in the field scale. And I think here still, again, as proposed, I think we need to do two things, right? Because for the field scale, you have the vegetation contribution, and that's a problem in order to get really soil moisture beneath the vegetation cover, right? Because what you have on top is the vegetation cover, and you like to get soil moisture that is beneath this vegetation cover. And like this, I think we need to account for vegetation. We need to extract this vegetation or get rid of it in order to get the contributions from the signals from the ground. So this is what is suggested. And I think a combination, let me say here, with IE plus physical constraints of IE, I think this is really the way to go, in my opinion. So we can better tackle soil moisture with vegetation. Let me say without vegetation, there are models and you can do it directly, estimating it, but without, with vegetation, we have still a problem.
Okay, is there one last very short question? Okay, then I suggest that we thank Irena once again and welcome. Thank you.